Welcome everyone to the second session of this morning. The chair for this session is Srijit Bhattacharjee from IIIT Allahabad. Srijit, over to you.
Thanks, Sriram. We have three talks in this session. The first speaker is Srashti from ICTS Bangalore. And I will give you a warning around 10 minutes, Srashti. Will it be fine?
Yeah, sure.
And for questions, for quick queries, the participants may unmute and ask. Otherwise, we will take up questions after the talk. So over to you, Srashti.
Okay, thanks, Shriji. So, hello, I'm a PhD student at ICTS Bangalore, and I'm going to talk about the search for lensing signatures in the gravitational wave observations. So, as you know, EM lensing has been observed in various phenomena, like we see the Einstein ring, the multiple images of the quasars, and distortion of the background galaxies and so on. And it has also allowed the EM lensing has allowed us to look far into the universe, map the dark matter distribution of the universe, and discover some exoplanets which could be rotating around the lens. Now, as light bends around the mass, the gravitational waves can also bend around and produce various phenomena and magnify the signals importantly. So in O3A, the first LVC search happened for the gravitational wave lensing, and I'm giving this talk on the behalf of LVK. So the in O3A, it consisted of four things. One is to see the lensing statistics, that how is the overall probability of lensing. The second thing is seeing that have we seen any events which have been particularly magnified in the O3A. The third is the multiple images search, which is if there is strong lensing, that is, if there is galaxy between the black hole merger and us and the detectors, then we could see the same merger in each detector multiple times, something like repeated events within the LEGO. And the fourth one is microlensing. So lensing can also behave like in wave optics regime, where we see distortions in the waveforms. So for the lensing statistics, given that we know the binary black hole population and lens population, one can predict the rate of lensing. And with the current knowledge, we find that 1 in 1,000 or 10,000 events are expected to be lensed and detectable by the current detectors. Further, as lensing gives magnification, it allows us to see much further into the universe. And at high redshifts, the rate of mergers, it's not constrained properly. So lensing can allow us to constrain the merger rate at the high redshifts. The complementary to this approach is also that since we don't have observed the stochastic background, and if we assume population models of the CBC, that we know the merger rate densities, and we use the magnification model for the lensing or the lens models, then one could predict the expected magnification distribution or the probability of observing magnification mu. And taking the merger rate uncertainties into the account, what one finds that probability of finding highly magnified signals is 1 in 10,000, and finding signals with magnification greater than 2 is 4, is little more. Now further, the second part of the paper was of the O3 research was also focused on trying to explain some of the events which are astrophysically falling under the mass gap. So this are the high mass binary black hole events which fall under this 50 to 65 solar masses, or the neutron stars, or NSBH populations which are falling under the lower mass gap. So what is tried is to explain that this mass gap could be because of the lensing, because the lensing has magnified those signals, and we are seeing bias in the source mass. However, when we analyze these events, one gets that to explain these events arriving from the magnifications due to lensing, one would need to get magnification of the order 10 for the BBHs, and even higher for Venus and SPHs, which is, as we saw, it's the probability is very less of finding that. So therefore, no compelling evidence of lensing magnification is found. The third one is the search for multiple images. So as I told, that if there is strong lensing, that is, if there is galaxy between us, and we could see multiple images of the same event, and the lensed and the unlensed waveform would be different by threefold. So as I'm talking about till now, one is the magnification, the another would be time delay, that we'll see these events after some time. And the third one is the Morse phase, which could be multiples of pi/2. Right. So with this threefold differences, what we will still find is that the waveform still looks like a BBH merger, but our bias would be in the inferred luminosity distance due to degeneracy with the magnification. Further, we'll see the coalescence time as different for the two events, and also we'll see the coalescence phase to be different, which is not really measured. While the parameters such as masses and sky location spins, we expect to be same for the two events. But it's hard to identify a handful of signals among thousands of unlensed ones at the current sensitivity. And to search for these strong lensed events, what is done is, the first one is the posterior overlap method. So to find whether a pair of signals that you have are lensed or unlensed, one constructs base factors, or let's say the overlap matrix, where one finds the overlap between the posteriors coming from data 1 and data 2. This overlap is taken over the parameters such as masses, sky, and spins, which are expected to be same between the two signals if they are lensed. Right, and the second thing is another metric is the R galaxy, which is the ratio of the time delay distributions. So if we had strong lensing, then we would have expected some time delay between the two events to follow some distribution. But if they were unlensed, we expect them to have other time delay. So based on the observed time delay, one can identify whether it belongs more to the lensed strongly lensed distribution or to the unlensed distribution. And based on this, out of 39 events, 19 event pairs, by 39 events, we means that the number of pairs would be almost square of this. And out of those 19 event pairs with high base factors were identified, and they were given for a more sophisticated analysis, which is joint parameter estimation. In joint parameter estimation, what one does is it also accounts for the Morse phase, in the sense that it takes both the data streams together, fixing under the lensed hypothesis, fixing the masses between each of the events as same, and the sky locations as same, and under the unlensed hypothesis, it would be different. So by joint parameter estimation, there are two pipelines which followed up those events. One is the Lal inference, one is the Hanabi. Lal inference is C-based, Hanabi is more Bilby Python based, and it also includes its hierarchical method. So after joint P, it also includes the effect of the source lens population priors, and also includes the selection effects, which is if our detectors are more sensitive to some locations and some masses. Now, based on this, after taking into account the population weighted population priors and the selection effects, there has been no confident detection for the super threshold pairs, that is the GWC TC2 events in the O3. Yeah. Now, the third one is one also searches for the sub threshold lensed images, which is that if a pair is strongly lensed or we have two copies of the signal, then the other copy, and then it could fall below our SNR threshold of 8. And what one does is to find those kind of signals with a targeted search. And as you know, that for if two pairs are lens counterpart, then they would be differed by three things. One is that there would be in some overall scaling factor. This is due to magnification. There would be some time delay. And the third one is there would be a more space. Otherwise, the masses and spins we expect to be the same. So what is done is one fixes to search for the subthreshold event, the subthreshold counterpart image. One fixes the mass of the template bank nearby. So let's say if for the super threshold event, that the detected event has a particular mass here star. So one searches nearby. Yeah.
Srashti, sorry to interrupt you. You have 1 or 2 minutes remaining. Okay.
Okay. Yeah. So one restricts their template banks to be searched near that mass parameters, and also the three restricts to the other three. I mean, only the templates are allowed to vary only over this three parameters, and the search is done with the GST-LAL and the PyCBC pipelines. And with this different searches, one finds the new triggers or new subthreshold potential lens counterparts of the detected events. And so with that, 8 new triggers were found, and 6 of them were classified as astrophysical. But when followed up with the joint P analysis, where one finds the Bayes ratio of whether they are lensed or unlensed, it was found that none of the pairs had significant Bayes factor, and in fact the highest one was minus 3.2 log Bayes factor. So here also no confident detection of lensing was found. The last part is when you search for the microlensing, which is when you have the lens mass which is of 100 2000 solar masses, and because of that the waveform distorts. It's no longer in geometrical optics limit, and one would see frequency dependent modulations into the waveform, which is this, and that modulation would depend on the mass of the lens, the position or the impact parameter of the source on the lens, and of course frequency. Now, as you see that as you increase or as you're more closer to the lens, the impact parameter is lower, then you see more distortions in the waveform. That is basically the beating patterns are arriving into the waveform. And to search for that, one constructs the Bayes factors for the microlensing versus unlensed hypothesis, considering the lens as the isolated point mass. And again, for the GWTC2 events, the base factors were not significant. They were almost all near to zero. Actually, log base factors was near to zero, and hence no microlensing effect was observed. So in short, these are my conclusions. I'll stop here for the questions. And I'll just say that the O3B lensing analysis in the process.
Thanks, Srashti, for nice talk. So questions? Yeah, I can see Arun has a question. Arun, please ask.
Yeah, hi Srashti, nice talk and nice kind of summary. My question is that how much is how large can be the delay between the source and the lens? For example, when you do a O3B lensing search, will you also look into O3A candidates in some of these methods?
Right, yeah. In the O3B, actually the full O3 is considered. However, if we have galaxy lenses, we expect the time delays to be order of months at max. But for galaxy cluster lensing, one could expect years also. But the probability of cluster lensing is lower than the just galaxy lensing.
Okay, thanks.
So are there any further questions from the audience? I don't see any raised hand. Just a quick question to Srashti. So can you please comment on what is the status of black holes as lensing agent? I mean, how massive black holes, the black holes can be solar mass black holes and up to few solar mass black holes, or it should be like very giant black holes. What is the status of that?
So any kind of black holes can get lensed. I mean, it's basically the gravitational waves that are coming from the any of the sources are getting lensed. But the strong lensing happens when the wavelength of the gravitational wave signal is much larger than the lens mass. And for galaxy lenses, you have strong lensing. Whereas if you have a 100 solar mass star or something which is in the which is acting as a lens, then it would be wave optics limit. You will see distortions in the wave.
Okay, thanks, Srashti.